it's the Valentine's Day, and then we have this reading assignment due, and then I plan to go over some of these questions at least because I was getting some questions about them. All right, let's see how it goes. So, the photochemical smog, okay, everything's okay with us. And here's the reaction and the energy diagram for that. This chemical process occurs in 2 steps. Okay. The first question is how many intermediate species are involved in the process? So no, this is the overall reaction. So we need to write the steps. Okay, we need to write the steps for this reaction now. That means writing the mechanism. Let's see if we can do it. Okay. So in the first step, we see that NO2 became NO and NO plus O, right? So step 1 seems to be step 1. So based on this, so here are reactants, so NO2, okay? And it seems to split into NO plus O atom. Okay, that seems to be the step 1. And then step 2, we have that O reacting with an oxygen atom reacting with another O2 molecule to give us O3. Okay, and then this seems to be the case because if we add these up, you see that we're going to end up with our overall reaction. Okay, so O over here is produced and consumed. Okay, therefore this should be an intermediate. No doubt about that. And then therefore that cancels out. So in the end, we're going to get, if we add the left-hand side, we have NO2 plus O2 on the left-hand side of the arrow. On the right-hand side, we have NO plus O3, okay, which is our balanced chemical reaction that is given to us here. Okay, so that is just making sure that that's kind of a sanity check more than anything to rewrite the overall reaction. Okay, but there's only one intermediate that is going to be O atom, right? So we're going to select that as the answer for that. Okay, so if I can do it, I need a different pen though. Okay, so the answer for the first question is it should be 1. So we're going to type 1. Let's see, back, and then yeah, there you go. So we should type 1. Anyway, the rate limiting step is determined by the step which has the highest activation energy or the slowest step, right? So in this in this mechanism, we have 2 steps. The first step has an activation energy of 306. I am not annotating here because I'm not using a screenshot. But second step, activation energy is only 107. Okay, so as a result of that, we know that the first step has to be the rate limiting step. Which step is the rate limiting step in this process? It should be first step. So you're going to write first step as the answer. All right, so the rate law based on this proposed mechanism. So remember, this is the proposed mechanism or theoretical. Okay, this is theoretical here. And so we are coming up with the theoretical rate law here. All right, so anyway, so we know the first step is the rate limiting step. Oh, if I can have the previous, maybe not. The screenshot. That would be wonderful, but that's okay. If it's not the case, we can rewrite it. All right. So anyway, so let's take another screenshot really quickly, and then we can write the 2 steps. So step 1, NO2 splitting into NO plus O, and then step 2, that O, that intermediate reacting with O2 to produce O3. Okay, so we know the first step is the rate limiting step. We have high activation energy barrier, and then for that compared to the second step, that's how we know the slower step. And then based on that, the entire rate of the reaction will be determined by the first step. Therefore, we can write the rate law for the first step, which is great because there are no intermediates, because on the reactant side of the first step, there cannot be intermediates, right? So we can write the rate law. Rate is equal to rate constant time. This is the rate constant for the first step, and that should be NO2 to the power of 1, because the coefficient here is 1. Okay, and remember, we only do that with theoretical rate laws. When you write theoretical rate laws for individual steps, okay, the coefficient of the reactant becomes the order or the molecularity, okay, and then goes here as the exponent. Okay, so we can just write rate is equal to K time rate constant times NO2 concentration. So okay, now let's see. So that should be option A. Yeah, so far so good. Topet agrees with us. Anyway, concentration effects on the rate. Select the graph that represents the variation of the rate of the reaction with the concentration of oxygen. Okay, so our rate low did not have any oxygen in it. So you know what? Take another screenshot and go here. So we wrote the rate low to be rate is equal to K, lowercase k times NO2. Okay, and we know oxygen is a reactant, but with respect to oxygen, the order is 0 because it is not in the rate law. In other words, the order should be 0. Okay, because anything to the power of 0 is 1. It's just multiplying everything by 1. Anyway, so if that's the case, what tells us is the rate of the reaction does not depend on the O2 concentration. Therefore, we should see a graph like this. That should be the answer for that. Okay. Now, yep, that seems to be the correct answer. Okay. And then temperature effect. Estimate how many times faster this reaction in the afternoon, 30 degrees Celsius versus 10 degrees Celsius. Okay. Then in the morning. Okay. All right. So to do that, we need some information, activation energies and stuff like that. Let's go back to, let's take a screenshot and do this 30 degrees and 10 degrees. You remember that? 30 and 10 degrees Celsius. Okay. So going back here, let's screenshot and work with that. Now, this is coming from the Arrhenius equation. We don't have to derive anything. Okay, you can use the equations as it is. So Arrhenius equation, if you write it 8 times Arrhenius constant or Arrhenius coefficient times minus EA over RT. And then with this in class, we derived an equation for equation to use to compare 2 different temperatures, rates at 2 different temperatures. The idea is when you so we know rate is equal to rate constant times to concentration, in this case the reactant concentrations, right? But when it comes to change in the temperature, for the first approximation, we know that it's not going to change our concentrations. What it's going to change is the rate constant. So if we have rate 1 with the rate constant 1, NO2 will be the same. rate 2 with rate constant 2, and node 2 concentration with same. This is just a little bit more information than you need. I just want to mention this here anyway. You see that rate, if you want to know rate 2, ratio between rate 2 and rate 1, that should be K2 over K1, because in node 2, the concentrations of the reactants cancel out, right? So anyway, now if you write the Arrhenius equation 2 times, so K1 and K2, we know that we can write an equation K2 over K1 is equal to e to the power of minus EA over R. While I'm doing this, I'm trying to, derive this in my head as well. Anyway, and then it should be 1 over T2 minus 1 over T1. Right? Now, in this, we know the activation energy, which is, let me use a different color now, this guy over here. Okay, and we know T1 is 10 degrees Celsius, meaning 283 Kelvin. Remember, we need to convert this to Kelvin. The temperature needs to be in Kelvin. Otherwise, our units don't match up. Okay, and then T2 must be, I think it's 30. So it should be 303 Kelvin. Okay, now we got that. Okay, so we know the T1, we know T2, we know activation energy, we know R, we can find the ratio. So that tells us how many times faster the reaction is at T2 compared to T1. So let's plug and check these numbers. That means switch to blue one more time. This blue seems to be more, I mean, it seems to be easier to see. Seems to see. Anyway, so if you plug and check the numbers now, K2 over K1 is e to the power of, I'm going to need a calculator. As you know, I don't have a calculator handy, and so I'm going to use Excel or something like that to do this. But that's okay. We'll use what we have. All right. Anyway, so it should be minus. Activation energy is 306.5. 306.5. I'm going to multiply that by 10 to the power of 3 to be converted to joules, and divide this by the gas constant, which is 8.314 joules per mole per Kelvin. Let's call it per Kelvin because I already took care of moles here. And then in parentheses, I have 1 over T2, which is 1 over 303 minus 1 over 283. Okay, so this should be the units here must be 1 over K. For everything in parentheses, the units must be 1 over K, or K to the power of minus 1. And you know that that's going to cancel out with this K over here, and then this J will cancel out. And that's how we're going to get a unitless number here. So let's see the number. So I mean, there are two ways we can do this. We can just plug and chunk all these numbers together in a calculator, or we can do them in chunks. So let's do them in chunks because it's easier for me to explain when I do it like that. So I'm going to do the temperature part first. So we have 1 over 303 minus 1 over 283, and that gave me a negative number. Obviously, this part gave me negative. Let's see, I have 0.00023332, so I can write this as it is, or we can say 2.0 3 times 1, 2, 3, 4, 10 to the power of minus 4. Okay, for that. And then for this part, okay, I get, let's see, I have 306.5. Oh yeah, multiplied by 1,000. 1,000 divided by 8.314. Okay, that gave me a large number. And that is 36,865.5. Let's write that like this. It should be 3.6865. 6865 times 10 to the power of 1, 2, 3, 4, 10 to the power of 4. This is cool, right? The reason is 10 to the power of 4 cancels out with 10 to the power of minus 4, which is great. So if I do that, these two kinds cancel out. And then all I had to do is multiply this number, okay, by this number. Don't forget this is going to be a negative. There's a negative sign in front of them, okay? Should be to the power of it. All right, so let's keep doing this. So it should be to the power of, now I need to multiply these two numbers. I have 3.6865 multiplied by 2.33. I get 8.589. Okay, so I get 8.589. So here's the thing though. So I'm multiplying two negative numbers here. So it's going to become positive. So what I can do is I can write that number directly here now. That number should be 8.589.545 or something like that. Okay, 9545. Doesn't matter. Okay, anyway, so now we need to determine the value e to the power of 8.589.545 is 5,375. This is 5,375.16. This should be your answer. Okay, so K2 over K1 must be that. Okay, now let me do something here. Okay, so let's see, 5,375. Okay, here. Okay, now let's check the answer now. 5,375. If you go back here, so should be, anyway, so top hat has it wrong. It should be 5,375 as we calculated it. That's the final answer. So anyway, so this will be changed. So it needs to change. I have a feeling that if you take the inverse of this, you'll get that number, but that's because top part is wrong. But anyway, I'm going to try that. 0.0001822. Yep. Yeah, exactly. Okay, anyway, so yeah, this answer here is wrong. It should be, the correct answer must be 5,375. We already calculated that. That's the correct answer. So that will be fixed. I think I can fix it. Okay, now moving on to the next question. Concentration effects on the rate. Select the graph that represents the variation of the rate of the reaction with the concentration of ozone. So ozone is not in the rate. Oh yeah, so this is a different reaction. Okay, ozone. Okay, anyway, let's see. This is a single step process, so that's the key word here. Okay, so single step process with an activation energy of that. Now let's do that over here. I'm going to take a picture. I don't know why, but let's take a picture so that I can write on it. Single step. Therefore, if you write the rate law for single step processes, it's like an elementary step now. Rate law must be an O times O3. Okay, so between rate and O3 concentration, it's a 1-to-1 relationship. When O3 concentration goes up, rate goes up. Okay, 1-to-1. Anyway, so that is going to be something like option 4 over here. Okay, not 3, not 2, not 1, it should be 4. All right, so that is that. And moving on. Oh, last 2 questions. Temperature effects on the rate. Estimate how many times faster this process is in a hot night at 25 degrees Celsius than in a cool night at 5 degrees Celsius. So it's a similar calculation like before, which is good practice because this is what you should be able to do. Oh, I need to make the temperatures, right? Okay, 25 and 5. 25 and 5. Don't forget those numbers. Again, let's do it. 25 and 5. Okay, so once again, it's about using Arrhenius equation and derive the relationship between the rates at two different temperatures, which we already did. Anyway, so that looked like you know what? Why don't we just derive it here so that it doesn't take that long? K is equal. You don't have to do it. You can just directly use the equation RT. This is 1. This is 1. And then K2 is A e to the power of minus EA over RT2, 1, 2. So if you divide 2 by 1, you're going to get K2 over K1 to be. So A cancels out. Then I have e to the power of minus EA over R. And then from the second equation, I'm going to have 1 over T2. And then from the first equation, I have 1 over T1. So this should be the relationship that we're going to be using. So again, let's do the same thing. We are just repeating ourselves, but that's okay. K2 over K1 must be e to the power of activation energy is 12.5 minus 12.5 times in the power of 3 joules is the activation energy. And then divide this by the gas constant, 8.314 joules per mole Kelvin. And then the temperatures, the T2 is 25 degrees Celsius. That should be 298 because 273 plus 25 is 298, I think. Minus 5 degrees Celsius is 278 minus 278. It should be, again, this is Kelvin, uppercase K, because it's after load Kelvin. Anyway, and then K cancels out, G cancels out. Again, we have this number over here. It should be, let's do the temperature first, like we did before. Okay, so temperature wise, we have 1 over 298 minus 1 over 278. That is gonna be again the negative number must is negative. Okay, I need to make sure that I get this right. 298 minus 278. Okay, anyway, it is 0.000. This time I'm going to use it as in the normal notation, not a scientific notation. Not in the scientific notation. This should be 24 because some of you might do this. And then if you do the other part, we get let's see what we have. Well, 0.5 times 1000 divided by 8.314, 1503.5, 1503.5, 48809, but this is 5. We don't want to split hairs here. And then again, remember this is negative e to the power. Okay, so that still stands. So we need to multiply this number by this number over here. We're going to end up with a positive number. And then it's going to be, let's do that too. 1503.5 multiplied by 0.00024 is okay. I'm getting, yeah, this is still a positive number. 0.3610. Okay, let's write that. 0.36084. Let's write that anyway. 84, and then e to the power of the number 0.36084 is 1.43. Yeah, 1.4345. We should check the numbers. 1.4345. So K2 is, or reaction 2 is 1.43 times faster than K1. Not a big difference. Yeah. But that's the number we get. 1.4345. Okay. 1.4345. That's better. Okay. This time top had got it correct. It's 1.4345. So that should be the answer. All right. So we got that right. We got everything right, actually. I mean, the only thing is top had got one incorrect. But let's do the last one as well, because this is switching gears here, because all this time what we did was a kinetic analysis of these reactions. And then in this case, they're asking us to do the Kp. Estimate how many times larger is the equilibrium constant Kp of this exothermic process during a cool night at 5 degrees than hot night. Okay. Now, all right, I do not think that we are going to do this now. The reason is I'm not going to test you on anything like that. So what we want to do is we need I mean, let's see what we have. Same temperatures, right? 25 and 5. But let's not get into this too much. Okay. All right, so what we have is we know delta G is equal to minus RT ln K. Yeah, for ln K is equal to minus delta G over RT. Okay, and then delta G, we did not do this in class or anything like that, so you're not gonna see this in quizzes or exams, something like that. But this is it. This is the relationship we want, and we know delta G is equal to delta H minus T delta S. Okay, if you divide everything by RT, okay, you're going to get delta H over RT minus delta S over R. Right? So ln K is ln K, let's say at temperature 1 is delta H over RT 1 minus delta S over R, and then ln K2 is delta H over RT2 minus delta S over R. Okay, and don't forget, we need to multiply everything by the negative sign here. Okay, so this should be minus, this should be positive. E to the power of minus delta H over RT plus delta S over R. Okay, and then yeah, actually we could have kept it there, but it's okay. And then K, uppercase K2 is e to the power of minus delta H RT2, RT1 plus delta S over R. Okay, and then if you take the ratio between K2 and K1, K2 over K1, it should be e to the power of minus, okay, so what we want to do is we need to, okay, let's write them out all together. We have delta H over RT2 plus delta S over R. Then we have minus, okay, because when you subtract, when you divide, you subtract. We have minus delta H over RT1, and then we have plus delta S over R. Okay, and then you see that delta S R is going to cancel out, and then we can rewrite this, should be e to the power of minus delta H over R. I'm going to take out. Okay, if we do that, we have 1 over T2 minus okay, that's this minus sign over here. Okay, minus 1 over T1. Okay, now we have everything that we need to solve this. Okay, so we have, yeah, let me make sure that I have space here. I feel like I'm gonna run out of space soon. Okay, we have E, and then we have negative delta H, which is 199.5 kilojoules per mole. I almost want to make it at 2,000. Anyway, let's call it, it's okay. It's negative 199.5 times to the power of 3 joules. It divide this by R, which is 8.314 joules per Kelvin. Okay, and then we have the temperature, okay, which is 1 over T2, 1 over, I think it's 25 degrees, which should be 298 minus, and then 5 degrees, 278. Okay, so again, as before, the Kelvin cancels out, joules cancel out, you have these numbers, and then we'll do this separately. Oh, we kind of did 1 over 298 minus 1 over 278. Where do we have it? Okay, I think I have it. That was negative. This number was negative 2.4 times 1, 2, 3, 4 to the power of minus 4. And then on the other hand, we have, I need to do that part now. 1, remember this is yeah, so this part is a negative number. Okay, then we are multiplying another negative number, minus 199. Okay, so I'm gonna keep that clear. we have minus 199.5 10 to the power of 3. Okay, and then divide that by 8.314. I get another negative number. This is negative, oh, again 2.4. Wow, that's amazing. Anyway, negative 2.4 times 10 to the power of, we have 1, 2, 3, 4. 10 to the power of 4. Cool. Okay, and this entire thing, okay, now we multiply these two numbers. Okay, and then this entire thing, we have a different color. Okay, should be multiplied by -1. That is this negative sign over here. Not a lot of negatives. Anyway, so and then we need to raise this to e to the power. I need to. Okay, so the good thing is to the power of 4 cancels out with to the power of -4, and it's like 2.4 squared now, right? So minus 2.4 times -2, negative 2.4 times negative 2.4 is, yeah, I'll give you the number. 2.4 times 2.4 times 2.4, 5.76 is a positive number because negative times negative is positive. And then we have still negative sign here in front of that. This should be e to the power of negative 5.76. Now, what is that? You can estimate that is going to be e to the power of minus 5.76, which is 0.00315. 0.00315 must be your answer. Okay, let's try that. 0.00315. Okay, 0.00315. Okay. Which was larger equilibrium constant Kp of this equilibrium during the full night. Oh no, yeah. So this is the other way around. Now, so what we did was we did the ratio between 25 versus 5 degrees Celsius in our calculation, but they're asking how many times this equilibrium constant is larger at 5 degrees compared to that. So 0.00315 is our answer. If you take, let me show it to you. Okay, so K25 over K5 is 0.00315. Okay, but they're asking K5 over K25, which is going to be 1 inverse of this, 1 over 0.00315. Okay, let's see what number we are getting. So 1 over 0.00315 is 317. This is 317 point something, yeah, which is closer to what they have over here. Yeah, so that's how you do that, but we are not going to be interested on anything like that. Okay, so I hope this helps. See you guys in class. Bye, everybody.